Let's start off. I just want to complete a couple of things. So I showed you that you can represent symmetries of each of the classes in the following way, and I showed you that these are reducible representations coming from these Schultz multiplier tables and so on. Okay, and then I had also pointed out the structure of the Hamiltonians in each of these classes, and I have discussed this section. This column I have discussed, and what is shown here is what happens if you exponentiate the Hamiltonians and run over all the Hamiltonians in that space. Okay? And what you see here are what are called as the symmetric spaces. The spaces, so if you exponentiate the Hamiltonian in each of these classes, you will actually map out some kind of manifold in some high dimensional space, high meaning that L is involved there, right? And they will turn out to be symmetric spaces. And in fact, all the 10 families of symmetric spaces will appear here. And those are those symmetric spaces. So the U Schrodinger of T is the time evolution operator. I had going the wrong way. Yeah. Okay. Yeah. Okay. Let me just flash 2 transparencies to advertise the work of my friends. So Arijit and Adeep have actually classified or put down the structures of Hamiltonians of any arbitrary n-body interactions in any of these classes. And so this is for when n is odd, and the next one is for n is even. Okay, all right. So today what we will do from now onwards is we will move from the symmetry business, and we will introduce topology and how the symmetry has something to say about the topology. And because of all the discussions we had, the script has been completely rewritten. So let me start with the new script here, right? Okay. Okay, so let me just okay. So what we'll do is we said that we had this L orbital system. And first I'm going to construct some kind of random lattice model, right? So what I have is I have some space, and the space is d-dimensional, right? And I have a bunch of points, right? Some set of points which may have some coordinates and so on. And let me just call them as some Ri. If this is the ith point, it has some Ri or something, okay? Some totally random set of points. And at each of these points in space, I keep one of these systems, right? So there is a GFS at every point like this, right? So I can create electrons at site. So to say, if this is the site I can create fermions at site I by this this matrix psi diagonal. Okay, and now the way I'm going to implement every symmetry that I have is by saying that it doesn't mix with this I index. What I mean by that is any symmetry now is written like this. This symmetry is on this full Hilbert space containing all the sites, right? All the sites. But the way I'm going to implement the symmetry is that when I do this, it will not mix these I labels. It will come back to itself with some unitary operation, unitary whatever it is, right? So I'm going to do that, right? I should write that. Okay, so in fact, all the topological insulators, etc., that you saw in this periodic table, they actually are of this kind. There's no mixing of this internal symmetry with anything else, right? So that's what happens, and I will write it as some U, right? This may be psi or psi dagger, psi transpose, depending on whether it is a transposing or the usual symmetry, right? So again, this may be a U or it may be a star, right? Depending on what it is. But the point I'm trying to say is that if I do a symmetry transformation, stuff at I will stay at I. It will not go elsewhere. Right? So in some sense, it's like a product. The group is like a product of whatever can happen in the I space and that. Okay, very good. This is our starting point. Okay. Now, what is the most generic Hamiltonian I can write on? Very simple, right? So what I do, I will just say sum over I and j. I will write a quadratic Hamiltonian like this. I'll just give it index I, j, right? And This is psi j. This is the most general quadratic Hamiltonian I can write. Right? I make no assumptions. Right? Okay. The only thing I need to ensure is that this is Hermitian. Therefore, I will get the following restriction. Hji will be equal to H dagger ij. Right? This is all I need. Okay? So I have this. Okay. Now, what I'm going to ask is, if I have different types of symmetries, how will that constrain this Hij? If it is at a single, if there was just one I, then we have already seen it this one, right? Okay. So without spending time, let me just lift it off of my notebook, and I will just write it down. So if I have a T-type symmetry, if I have this T-type symmetry, then it will constrain Hij in the following way. Under the action of T, Hij will go to Ut H star Ij. Right? That's what it will do. Okay? So the symmetry condition means I will have to equate this to that. Right? That will be the symmetry condition. Okay? And let me write down the things for C as well, or I can just leave it as an exercise. So this will turn out to be minus UC H star I comma j to dagger C, and for S it will be minus UC H ij US. Right? So what do I need? If I have n sites now, there are n square L by L Hamiltonians, L by L matrices, n square of them for each I and j, right? And they will be constrained in this, they will be constrained like this just from hermiticity, and they will be constrained in this fashion further if there are these additions. Everybody is good with this? Right? This is straightforward discussion. Okay. So now this is totally random. There's no structure in this way these I's are placed, etc. It's completely random, and we can actually analyze this, but we won't. Right? Instead, what we will do is, we will put this on a lattice. And the simplest lattice to put it on is the D cubic lattice, right? Since I'm in D dimensions, I will put it on D cubic lattice. I could put it on more complicated lattices, but let's keep life simple. Right? Okay, if I do that, then can someone tell me what will happen to the structure of this Hamiltonian? And I want to have lattice invariance, lattice translational invariance. If I want to have lattice translational invariance as well, what will I do to this Hamiltonian? Sorry? No. But if I were to write in real space, what will I do to it? Okay. So what will happen is, you will see that in a lattice with some translational symmetry, right? What will I get? I will get something like this. Psi dagger I, and this becomes Hi minus j. Right? Because it will only depend on the distance between, or the vector between these two. Right? Something like this. Okay, this is what happens, is summed over I and j, of course. Okay, and just like Abhiram was just saying, we can immediately go into K space. I can have these xeroxed and passed on to you if needed. I will not get into all the technicalities, just let me write down the answer so that we can go ahead with understanding the important concepts. Right? So this, then when we go to momentum space, right, what do we get? We will get 1 by square root n. Sorry, I don't need all this. Skip that. So what I will get is, I will get H is equal to sum k, psi dagger k now, and H k, psi k, right? Okay, all right. Now let me just quickly make sure that everybody is following me. Suppose I take this Hamiltonian and impose any of these symmetries, right? What do you think that will do? So this is a generic Hamiltonian. It's just translational invariant. Now I demand these symmetries. let's say if I demand time reversal invariance, what do you think will happen? Nothing. No, but no. Let me just ask you this. What do you think this object is? The math, what is the structure of this object? It's an L by L matrix. We are on the same page, right? Okay. So under the action of time reversal, will this be completely unconstrained as a function of k, or will there be a new constraint that will show up? See, in the real space, there's a constraint that's showing up, right? So that will translate to some constraint in the right. Okay, so let me just write down. Now that I've given you the hint, you should work out the math. So what happens is, in the t case, you will find the following is true, right? hk is equal to whatever your ut was, h star minus k ut dagger. And you have actually seen this. Jay has actually shown this many times throughout his talk, right? Okay, and if it is, so let me just write t here. If it is c, you will again see that there is a uc here, and then there is an h star minus k again, and uc dagger. This is for c, and then you will see that there is a us hk u dagger s. S. This is for the S. This so you will get additional constraints. Okay, everybody's seen this, at least understood what is being done here. Okay, now the important thing to notice is that for the sublattice symmetry, there is the minus k part is completely unconstrained. There is only constraint at the very same k, right? Whereas these guys, whatever is happening, so if I were to draw the Brillouin zone as a square, right? I will soon draw it as a torus, right? If something happening here is related to, this is k and some minus k, these two will constrain what happens here and what happens here. Right? Whereas the sublattice, it doesn't, every k is sort of independent. It's at the very same k that you will have any structure. And you can see immediately what the structure is, right? Because US, we know, is 1 PQ in the canonical representation. 1 PQ is that one identity on the first P and the -1 on the other Qs. You will see that this will again have the structure which is 0 on the diagonal P's and 0 on the diagonal Q's, and it will only mix P and Q. So that structure will be imbibed into the K space as well. Everybody's understood what I said? So if the symmetry is there, H will look something like this. HK will look something like this. It will look like H dagger K, HK, H dagger K. And this is PP and Q. So that's what this will imply. Right? Okay? All right. Yeah. Yeah, you just use Fourier transform. This is in real space without any translational symmetry. No, Abraham, actually you can do it very straightforward, no? Just put I minus j, and write 1 by square root n sum of e to the ik. Just compare for each k. Yeah. It's very straightforward. I mean, you can do it. Yeah. All right. Okay, so what do I have here? I would have some L bands for if I diagonalize the Hamiltonian, I will get L bands, right? And let me just schematically draw this Brillouin zone and some set of bands, right? Okay, and this is the energy, and this is K, and this is the zero. Okay, so this is what I will typically get out of any consideration like this. Okay. What is the space in which I have these wave functions living? Right? That's the d-dimensional Brillouin zone. Right? The d-dimensional Brillouin zone has what geometric or topological structure? A one-dimensional Brillouin zone is what? It's periodic, right? A one-dimensional Brillouin zone is what? So this is, I take this, right? And I have to identify these 2 points. So this is minus pi and this is pi, and I identify these 2 points. So what will I get? What is a geometric object if I take a string and identify 2 points? I'll get a circle, right? Right? I'll get S1 as it's called. It's also the torus of 1 dimension. So we'll also call it T1. Right? It's identified. Okay. Now suppose I take the square boson, right, and identify these 2 points, these 2 lines. So what do? I take this, stick it around, and I take that and stick it around. What will I get? I'll get a torus, right? So this is T2. So the d-dimensional Brillouin zone, right, with something, right, is TD. Right? So this TD is what I will call as the base manifold. So this is the manifold on which we are going to live, and we are going to attach things on it. Okay? So this is what we will call as the base manifold. Okay, now there were several questions, and Jayanandra had asked about the number of orbitals and all that. So I will show you that by very same considerations, we can go to a field theory. Okay, so let me very quickly show you that. So what I'm going to do now is that instead of these points being discrete, right, I have real space in d dimensions. Right? Completely real space in d dimensions. So what I'm going to do is, I'm going to make this guy just R like this. And at every point in space, I have a GFS. Right? And I'm going to implement this symmetry like this. Right? So again, the symmetry, the intrinsic symmetries do not talk to this other direction that we have done. So how will I write my Hamiltonian now? So you see, I can use the chalk to great effect. So what I will do is I will write something over dr and something over r here, and then something over r prime here. Okay, let me just use a slightly different notation which I will then prepare. And then there is r, r1, r2, let's say. Right? R2. Right? And the hermiticity condition you can immediately write down, right? It's very easy to write that down. So this will be just R1, R2, and this is R2, R1. Right? You can easily write that. Okay? So what do I need to do? I need to integrate this over R2 as well, right? And just for dimensional considerations, I just have to multiply it by the volume of my sample, the big volume of my sample. Right? Because I have 2 volume elements, energy density. So I need 1. So I just do this. So this is the Hamiltonian. Okay. Now what I do again, I can write different kind of symmetry conditions, etc., which I will not get into immediately. What I will do is I will do the following trick. I will write R1 is equal to R plus delta by 2, and R2 is equal to R minus delta by 2. Right? You can immediately see that this thing will become something like this. dr integral d delta, right? Psi dagger r plus delta, h r comma delta. I'm just writing like this, r semicolon delta if you like, because it's actually, I'm just doing a variable transformation. So I get function of 2 vector variables, which I just write like this, right? And then this is psi dagger r minus delta by 2. Okay? Thank you. Okay, and then there's of course this 1 by 1. Okay? So now, for example, if I want to look at, if I feel, or if I know from some physical considerations, that this is like a hopping matrix between r, something at r and something at r plus delta. So suppose I just, have some physical intuition about the system that I'm interested in, that this delta is somehow small in that the hopping dies down at some finite delta or something like that, then I can actually construct a field theory out of it, keeping only the slow degrees of freedom, right? And let me show you how to do that. So what I will do, I will take psi dagger r plus delta by 2, and this is equal to, I just write it like a gradient, psi dagger r plus delta by 2 dot gradient psi dagger, like this, right? And I substitute this back into this. So what will I get? I will get the following Hamiltonian. Oh, I should not have erased that. Okay. So you can see what has been erased, right? Even if I write over it. I hope you can. I asked for it. Thank you very much. Thank you for your kindness. Okay, all right. So I put this into this, and what I will get is, I will get a bunch of terms like this. I will get h dr is equal to psi dagger r, and let me just anticipate something. mr, this is a matrix, right? Psi dagger r plus, I will get terms like this. Del gradient, sorry. Yeah, I should write it carefully. I will write it something like this. Gamma of r vector dot gradient psi dagger psi r plus, there is a Hermitian conjugate term which you can write down, right? I will not write that down here. Plus, there is a term that looks like this, gradient psi dagger. There is another term which will, let me call it as some lambda, which is also a matrix. It's actually a tensor, so write it down like this, of r. This is a function of r, and this is gradient psi of r, etc. Right? So what are these matrices now? You can just see m of r is simply equal to 1 by v integral d delta h of r delta. Right? So what did I do here? I took an expansion like this, stuck it in here, and I did a similar expansion for that, and I took one term out. Right? The leading term, the term with no deltas coming from the operators. Right? Then I took the linear term, and I got this. So you can see that gamma of r would then be equal to 1 by v integral d delta. It's a vector delta h of r delta, right? And this lambda, which is a tensor of r, would be equal to 1 by v integral d delta. This will look like something like this, right? I may have missed some signs in this, but that's not. I mean, I've committed bigger crimes here, right? Okay, all right. So you can see that you can get a field theory out of this, right? So if you decide that the higher order, you can see that you're calculating the moments of this object on this h of delta. So if that has some finite support on delta, then the higher moments will start dying. So you can drop all the higher order terms and maybe stop. Okay. So now I want to ask you a question. Have you seen any Hamiltonian in this school that looks anything like at least some of the terms here? I thought that's what you did in the first lecture of Jayendra, right? So if you look at the Landau level problem, you can see that has the structure like this, right? There is like p minus a, so you'll get a p square term, a gradient term, and you'll get some potential kind of term, right? It's all there here. So you can see that all the examples that we have discussed can be cast in this language. I hope that's clear, right? That's clear, right? Yeah, you can see that it's there. Okay. So now what I'm going to do, I'm going to discuss clean systems. There's no spatial variation of any kind. So what should I do to discuss clean systems? So this is a general system. If I want to discuss clean systems, what should I do here? Translationally invariant systems. What should I do? Use the eraser. Let's do this. Done, right? Take it a clean system. right? Everything is translational invariant. And then you can immediately write this as a Hamiltonian in K space again. Okay, let me just, I need the K space there. Let me just go the continuum version of the problem. Let me just use the continuum version here. You will see something else going to come here. So you can see that the continuum version can always be written like this, something like this, dk psi dagger k hk psi k, something like this, right? Okay, so now I ask you the following question. What does this k run over? So you all agreed that in the lattice case, k ran over this torus. What does this k run over? Am I in the forbidden zone? I am. Okay. All right. Let me just write it here. Sorry. Oh, maybe. Okay. This is what it is. So what does this guy run over? Okay, let's just consider, let's consider one dimension. What does it run over? Okay, so you want to use an ultraviolet, you want to use a maximum K. Right, so you want to have a cutoff, right? But at the end of the calculation, you want to remove the cutoff, right? Always, right? Okay, so even one dimension, what is the object? What is a geometric object even with a cutoff? String, right? But suppose I were to run the cutoff to infinity, what is that object? This guy goes to plus infinity, that guy goes to minus infinity. And suppose I identify the infinities, it will become a circle again. Not bandwidth. I'm letting the cutoff go to infinity, and I'm identifying the point at infinity. This is what we do in complex analysis. You remember that when we did complex analysis, there was one point at infinity. So the plane, for example, could be mapped to the sphere, right? So in the limit of volume going to infinity, Vd going to infinity, this space, the target space, is the sphere in d dimensions. In 2 dimensions, it will be the plane, but I identify all points at infinity, so you just wrap it around and identify it like this. Right? You understand what I'm saying? Right? So this is a very standard trick in field theory. Okay, yeah. Okay, let me not. That's topologically good, but mechanically, the metric is important at places, right? Elasticity is important, it's not just topology. Okay. No, that is a lattice problem. But that means I will be, it's okay, that's fine. I mean, that's more or less like what Abraham was saying. So suppose I were to restrict myself to something here, then I could view this as that I could do an approximation. I could. Right. But I could legitimately start with a field theory with no attachment to anything lattice. So in that case, the base manifold is SD, the sphere in d dimensions. Right? That's the base manifold. Yeah. No. Did you understand the torus? Here I don't have any lattice. So what is my K space? My K space is just the plane, for example, in 2 dimensions. And what I do, all points at infinity, I identify them. So what does that mean? So if this is the plane and this is the schedule, you'll be very happy when I crush it up, right? So you see, I just take all of these guys, and if these are all points at infinity, I identify them. What will I get? I'll get a sphere. So do that in any dimension. You'll get the sphere in that dimension. Okay, there is a very subtle argument for that. So the idea is that if we are you're going to let all the fields go to some constant values at infinity. So if you let all of them go to a certain constant values at infinity, right. We will certainly have a filled band in the lattice. It's a great question. I was going to ask that question too. Okay, all right. So, okay, thank you. Just hang on. Okay, so what Janendra is asking the following, right? So you see, I have these del square terms, right? For example, so I'll give you k square energies, right? So then, if I put the chemical potential anywhere, I'll have a metal, right? Except if you have lambda levels. So these guys have to have structure where you'll get these bands which are well separated and all. But there are Hamiltonians with those bands. Huh? Or you could have something where there are positive energies and negative energies. That is also possible, like a Dirac dispersion or something. So it can come out of this. So you can have a whole set of infinite bands below, infinite bands above, and you can have a zero energy and all of the bottom guys are filled. So there are many situations we can envisage where you will actually get an insulator, even in the infinite system. Okay, all right. I was planning to ask the question as we reach that. Okay, so what I have done so far is I have identified what are the base manifolds. All right. So now let me start discussing in a very elementary way what would be the ground state of the system. So I can now discuss both the continuum and lattice problems in complete, without addressing specific ones. I can discuss them in generality. So for example, if I solve this problem, right, the result of this will be L bands. Right? Whether it's continuum or lattice, it doesn't matter. You'll get L bands out of this. And what you will get is, I'll label the bands by E alpha k. So this is the band dispersion. And this is psi k alpha. And this will be psi k alpha again. And this is h k. So this is the solution. These are the, I set up the problem in generality, and then I'm showing you the solution here. Right? That's what I have done. So I get these bands. Now what I can do is I can do things formally, but let me not get into the formal thing. What I can do is I can try to see what are the filled states here and make sure that I have an insulator. How do I make sure that I have an insulator? Let me just write the following function, right? I will call O of x. This is occupancy. This is the notation for occupancy. Is equal to 1 minus 2 Fermi function of x, right? And this Fermi function is a zero temperature Fermi function. So it's actually just a theta function. Right? I'm just defining this function. And what do I do? I define a new operator. This is just h. Right? So what will that be? 1 minus 2 nf0 of x. So if I take this operator, it has the very same eigenstates as h of k. But its eigenvalues are either plus 1 or minus 1. If I'm in an occupied state, I have eigenvalues minus 1. If I am unoccupied state, I have eigenvalues plus 1. So effectively what I'm doing is, I'm just flattening out the bands. Right? I'm just saying that all occupied states are treated equally, all unoccupied states are treated equally. Right? Why do I do that? Because I know that I'm going to make the following assumption, that this thing will either turn out to be plus 1 or minus 1 for sure. What that means is I have no level crossing the 0, which means I have a gap system. Right? So the main thing here is I have a gap. System is gap assumption. Okay? So the eigenvalues of OH are either plus 1, unoccupied, and minus 1, occupied. Okay, let me just say it empty, and this is filled. Okay, So the picture of that is very clear. We have, let me just draw some zero of energy, and I have some filled bands and some empty bands. Right, and this could be, this picture could be either the torus or the sphere. This axis. This is either TD or SD. Right, that axis. And let me say that there are filled LF filled bands and LE empty bands. Okay? Everyone is with me? These are things that you are very, very familiar with. Okay. Now I ask the following question. What is the ground state of the system? The answer is, you know very well. You just take all the filled states, construct a Slater determinant out of them, and that's what it is. Right? Suppose I give you a ground state and a Hamiltonian in a certain class. Right? And I give you another Hamiltonian in the same class. Can I go from this Hamiltonian to that Hamiltonian in a way that the ground state evolves smoothly from this particular ground state here to the ground state of the other Hamiltonian smoothly? What do I mean by smoothly? Without closing a gap. Right? Gap closing would mean one of two things. Right? It would mean that a new band is coming in or going out of the system, or two bands could be crossing. Something could happen to cross bands. That's what typically gap closing would mean. Right? You can have this very complicated scenarios, more, you can have touching on one line, touching at a point, etc. All that stuff can happen, but it will, some kind of gap closing can take place. Then in such, we want to avoid such situations, and we want to ask, under what conditions can I take a wave function, the ground state of something, and move it to the ground state of something? Okay? This is the question. All right, now how do I construct the ground state of this? Okay? So this is the main point here. So you should pay very careful attention to what I'm going to do now. So you will find that if I take any two of you and ask you what is the ground state of something, it's quite possible that you will find apparently different answers. Right? Why is that? Let's just take a very simple tight binding model. Okay, I'll erase this in a minute. Let's take a tight binding model. Right? A Hermitian conjugate, and you will get some energy dispersion like this. Right? E of k equal to some C dagger Kc. And associated with C dagger, there is some block state psi k. Now, some of you may choose some particular phase for this block state. Right? Somebody else may choose an entirely different phase. Right? So I could choose this particular phase, or I could define something else, psi tilde k, which is equal to, this is the first person's choice and this second person's choice. And this could be something like e to the phi k times psi k. There is no difference, you will not see any difference in physics of this. By the way, you cannot choose phi k arbitrarily, right? Because say at the zone edge, it has to be smooth, so it has to be periodic function and all. So I assume that you will take care of all that, right? So you could choose a completely different phase, right? So somebody gives you a wave function, somebody else gives you a wave function. Even for the same Hamiltonian, they may look different, right? So I want to show you a picture and see whether you can see something like this. Okay? So this is a painting by a 20th century it's actually 20th century artist who will remain unknown forever. Right? Okay? So this is a two torus. Right? This is a torus with two holes. Right? Okay. What is this? So, okay, just imagine that I am pretty solid. I know you will object to that because you know my head is empty. So just for a minute, assume that I'm completely solid. And imagine that these two holes are the holes of the torus. Right? So the first picture I'm showing you is this. What is the second picture I'm showing you? It's this. Are they topologically equivalent or are they distinct? How many people vote for distinct? Yeah, I think people should vote well. So that's more than 50%. How many of people feel that they are equivalent? Why do you say that they're equivalent? No, but they're tied up like this. See, I can't. Thank you. That's absolutely right. It's correct. They're topologically equivalent. They're not distinct. This thing can be smoothly deformed into that. So the trick is like this, right? So, okay, I'll just draw a schematic picture in the forbidden region so that you will not see all the mistakes I'm making, right? So what is this? So you see, so you can just think of this as one of the handles, right? And this is the other handle, right? Okay. So now, how do you visualize that one of those other things, right? So what you do, you bring one of these guys, and you see it's entangled, right? It's sort of going in through this, like this, right? Now what you do, you take this end and push it through this. Take this end and push it through this. So I'm just doing this. So I pushed it through, it comes like this, it goes out like this, right? Now you just move this around, you'll get it. So this is actually topologically equivalent. Right? This is what we would call as a gauged, gauge related. This is exactly what we mean by two wave functions are gauge related. This is what we mean by they are in the same universality class. They look apparently different. You understand? So things that look very bizarrely different are actually the same. And you will also see the things that look very same are also bizarrely different. Okay, that we'll worry about later. All right. Okay. So this is the story. Okay, this is really the central idea of this topological business. So it's this gauge thing so if you want to compare wave functions of two Hamiltonians, you have to really worry about whether I can take one to the other smoothly. Like what I did here. This was all smooth, you see? I didn't tear anything or something. Okay? So let me give you an idea of what really is the wave function if I have L orbitals. Right? Okay. So let me go to a particular K. Now again, this can be either my SD or TD. There's a particular K. At a particular K, what are all the states that I have? Right? I wrote down some psi k's there, psi k alphas there. Right? I could write some wave functions for them. Right? So so this will be psi k alpha equal to 1, psi k alpha equal to L filled, psi k alpha equal to L filled plus 1, and all the way to psi k alpha equal to L filled plus L empty, which is equal to L. Right? I collect all of these wave functions in an array. What is the size of this array? L by L. Right? It's an L by L array. So Abba, since you said it's an L by L array, mathematically, what is that L by L object? Oh, sorry. I'm just collecting the states at a particular K into an array, right? So the array is like this, psi k alpha equal to 1, first band, the wave function of that, and then goes all the way to psi k alpha equal to L filled. This is an artificial place I'm putting this because I'm going to use something here, right? And then this is psi k alpha equal to L filled plus 1, and goes all the way psi k alpha equal to L, which is actually L filled plus L empty. Right? So this is an array. I'm simply collecting the eigenfunctions of the Hamiltonians in a particular case. So, it is a unitary matrix of size L by L. Okay, that's the message I want. So this object is U L filled plus L empty. This is an element of that. So this belongs to this. Okay? Everybody is good with this? what is the ground state if I just worried about just this guy, just this particular K? What is the ground state? What is the ground state? Slated determinants with filled ones, right? Slated determinants with filled ones. Are you sure? The answer is yes, you are sure. But then, why am I showing you this picture? But somebody else will say, who cares about your slated determinant? I will consider a new slated determinant. Huh? So what I will do, I will take this guys, right? Just this guys, psi k alpha equal to 1, psi k alpha equal to LF, multiply this by something, some matrix in L filled, and take the determinant of that. That determinant is same as the other determinant. Right? Because determinant of this UL is 1. This is the gauge degree of freedom I have. Right? But then you'll realize, oh, I can do this. I can also rotate these guys by whatever I want. They're not going to be occupied, but I can rotate them. Right? So there is something here which can also have L empty. So among all these possible wave functions, what is the ground state wave function? What is the space in which the ground state wave function lives? So among things here, I have to remove this gauge degree of freedom, and I have to remove this gauge degree. So the ground state at K is an element of the following space. It is an element of U L empty plus, L fill plus L empty divided by, that is cosetted by U L filled right? So generic wave function at a K belongs to this space. Everybody has understood that? I'm sorry? What do you mean? Why did I remove? No, look. See, I can, my ground state is this. But I can also, there is no reason why I should stick to this choice of this, for the set of all states there. I could also do U in those. Right? I will not occupy them. But the important thing is I'm not mixing the ones with occupancy value -1 and occupancy value +1. So I have gauge degree of freedom in the occupied guys, and I have gauge freedom in the unoccupied guys. So I have to remove all of that. It doesn't matter. But you see, that doesn't matter because this U has that information, right? How can you interchange LF and LE? That's off, right? And LF and LE comes from the energies, right? So what I'm saying is, okay, what is the statement? So there is so the state at a given point is some U matrix. Is that U matrix unique? It's not unique in the following way. If you give me a set of block functions, right? What I'm going to do is I will just mix the occupied guys within themselves, the unoccupied guys themselves. I'll get a new U matrix, which is the same physics as what I had before. So I have that freedom. So the object that I have at a point is this. What do you mean? Why don't you? Because then I will mix the states. Then No, but ask yourself, what is the starting point? What is the Hilbert space locally? So the Hilbert space locally was, so there is a gauge freedom, right? In choosing the Hilbert space, starting point Hilbert space. What are all those things which are equivalent? within the ground state that you want. That is what you should look for. What are all the equivalent things keeping this ground state of L-filled orbitals? See, I'm leaving something empty, right? But you see, that is not independent of the Hamiltonian. It's there in the Hamiltonian. So at a given point, what is how do I describe that thing in terms the state there, including the ground state? So I have to find all ways of writing this U matrix, which leave this sector and this sector unmixed, so that the ground state wave function is still the same old ground state wave function without this gauge transform. Which one? L filled equal to 0. Exactly. Exactly. Thank you. Yeah, there's no. Right. K. Are they for different cases what you're asking? No, what is the question? Sorry. For same K, they will be mixing, no? It's not, it's some general gauge. That will be like a diagonal. This U is like a diagonal. That will be like product of U1s. But I can do something more general. So then, if I know that if I'm going to describe, see, if I'm going to map a Hamiltonian, so what is the idea? The idea is that I'm attaching a Hamiltonian, HK at every point, right, on this manifold. How do I describe the structure of that thing? So that is given by, take all the states, and you want to also get this ground state correctly. So that you can deform the Hamiltonian and move in the manifold where the ground state is also fixed. Because otherwise I will be, how can I get the energetics? How can I show that there's No, it will change. No, if I mix a state with occupancy -1 with occupancy +1, then I will be linearly combining wrong energy states with so that's exactly the thing that I'm removing. So I have this matrix UL plus the total UL matrix, which has all the eigenfunctions. And I'm allowing any of these guys to be mixed, any of those guys to be mixed. But no crosstalk. If you crosstalk, then I will close gap and so on. Then I will be mixing, yeah. No, but I will be getting a orthogonal wave function which is not in the ground state, right? No, I'm not changing the Hamiltonian yet. I will change the Hamiltonian in a minute. It does not change. But you cannot make this part of the ground state. You cannot have any weight of this state into the Slater determinant ground state. So you shouldn't be mixing that in. So the freedom you have is you can mix any of these guys in, which we have collapsed to this -1. That's why we treat them all at this -1 thing. And all of these guys will go to +1. You can mix them, but you can't mix in between. If you like. Sure, absolutely. Sure. Okay? Okay, so what have I achieved here? So this is the ground state at K, right? Okay? So I have two cases. So this now we know is a coset space. I just showed you that this is one of the symmetric spaces, right? In fact, this particular coset space's name is called a Grassmann manifold, right? Okay? So what do I have? I have either the torus or the sphere. So this is the TD and SD. And I have this Grassmann manifold. Right? I have this Grassmann manifold, right? And what I'm doing is, I'm taking this guy and mapping something there. This is a particular K. From here, I'm taking an element here and attaching it here. Right? And the same thing, if I'm working about the continuum problem, I'm taking, at this point, I'm attaching some element here. Right? So what do I have? I have a map from my base manifold to this Grassmannian coset space. Okay? So what decides? Okay. If it's a lattice problem, it's a torus. It is lattice, it is torus. In continuum, it is sphere. In either case, it's a map from this base, whatever is the base manifold, to the Grassmannian. Right? Everybody's good with this? Okay. Just 2 comments. This is very complicated. That's the first comment, because if this Grassmannian manifold is some high dimensional thing, it's hard to visualize what it is. It probably looks like this, right? And second comment is the following. What I have done here is generically correct if I'm in the A class, which means I don't have any symmetries. Right? If I had symmetries, then I couldn't just arbitrarily map every point here to the Grassmannian. Because you see, stuff happening at K is related to stuff happening at minus K. So then with symmetries, there'll be more complicated mappings of this kind. Right? Complicated mappings with more restrictions. Right? But bottom line is that from this base manifold, there is a mapping to some kind of target manifold, the manifold of ground states. Right? So now the question we want to ask is, how many distinct types of mappings are there? Now that is not a well-phrased question unless I tell you what do you mean by type. Okay? And for this, what do you mean by type? So let me give you the answer first and then give you this. So the number of distinct, okay, topologically distinct map from the manifold, which is either from the base manifold, which is either TD or SD, right, to this Grassmannian, are actually characterized by something called as the homotopy group. So this is pi d of the Grassmannian. L filled plus L empty divided by U L filled, U L empty. Okay, now if you're fully with me, you will see that this should be surprising to you, right? Because in one case, it's the torus. So strictly, okay, I have to define what pi d is. Okay, I'll come back to this. So there's a little bit of a surprise here, okay? So all right, so let me explain to you what do I mean by homotopy, right? So this is called as the homotopy group. Okay? All right, so let's understand what do you mean by homotopy. So let's start with the simplest example, right? So brief digression. Right? Okay. So let me just start by something very simple. Let me just start with the line -1 to 1, right? This is the real line. Okay. And what I'm going to do is I'm going to construct periodic functions on this line, right? So what do I need? I need f of -1 is equal to f of 1. Okay? So can you give me an example? Okay, I will write out the example. So let me just consider f1 of x is equal to sine 2 pi x over, okay, 2 pi x. So when I'm x equal to -1, what do I get? I will get 0. And when I'm x equal to +1, I will get 0. Right? So this function looks like this. What does it? It'll be embarrassing if I get it wrong. Right. So I start something like this, and then it goes on. I think I got this right now. Yeah. If I get this right, I might actually be admitted to some PhD program. Okay. All right. So okay. So this is good. Now I give you another function, right? So which is f is equal to sine, let's just say 4 pi x, right? And you can see that this is some other function, right? Which is periodic. So I claim that these two functions are homotopically equivalent. What do I mean by that? I can smoothly deform, while keeping the periodicity, I can smoothly deform this function to that function, right? Without breaking anything, right? How do I see that? So what I do is, I define another function, g of x, and I have a parameter which tells me the deformation, right? This is t, which is equal to 1 minus t times f1 of x plus t times f2 of x, right? For any value of t, this is a periodic function. So I'm still always in the space that I want to be. And you can see very smoothly, I have some mathematical things, I'll show some better examples, right? Okay? Very smoothly we can go from this function to that other function. But if you see, they're apparently different because one of them will have 4 wiggles and the other will have 2 wiggles. But they're smoothly connected to each other. So this wiggle of this kind of function is not topological. You can, within our definition of topology, which is like you have to have periodic functions, this wiggle is not topological. Right? Everybody sees that? Right? So these two functions are homotopic. So for example, if just for a moment, just imagine that this were my SD, or the base manifold, and these were my wave functions. I would then say that this ground state and this ground state are topologically equivalent. Because they can be smoothly deformed from one to the other without breaking periodicity, which is equivalent to my condition of not closing the gap. Everybody's with me? Okay? All right? Anybody lost me? No, I'm just showing you some condition. I'm imposing some condition equivalent to what we are having before. Right? It's not, yeah. It's not energetic or anything like that. I'm just imposing a condition for defining topology. Why are you taking my question? I was going to ask you that. Okay, so this is a serious question, right? So actually you can show that if you're going to discuss smooth functions which are periodic, you cannot find any function which is not homotopic. You give me any two periodic functions, you can deform one smoothly to the other. So this kind of thing is topologically trivial. Anything in this can deform smoothly into the other. This kind of a map does not support any non-trivial topology. Right? You can just prove this yourself. Just take any periodic function. I just force them to be 0, but you don't have to be. You can put any periodic function you want. Take any other periodic function. You just combine this. You can smoothly go from any periodic function to any other periodic function. So what have I shown you? The space of maps from -1 to 1, periodic maps, are topologically trivial. There's only one class of them. Any function can be gotten to any other function. Everyone is with me? All right. So now, can you participate in coming up with a system or a model or a map or anything in which you can get topologically non-trivial things? Yeah, I wanted to bring an extra belt, which I did not, and I will certainly not, find an alternative here, right? Okay, so I need some strip of paper of some sort. Okay, so here is a nice strip of paper. Okay, so this is Janedra's homework problem. So without destroying a single question, right? I'm going to take a little bit of piece of, maybe I'll take a slightly longer piece of paper. I was hoping to bring a belt, but I couldn't find it at the last moment. Okay, and I'll show you some Mathematica things and so on. Okay, all right. Okay, so this is my interval -1 to 1, which I'm going to identify now. So it's S1, and what I'm going to do is at every point on S1, I'm going to attach a complex number. Let me push it a little further. I'm going to attach an element of the U1 group, which certainly is a Grassmannian manifold. Right? Right? Take LF is 1. Okay, sorry. Okay, may not be a Grassmannian manifold. Sorry. I have to check. Okay, it doesn't matter. Take U1. Okay? And so what can you, how do you visualize U1? Right? U1 is, you can visualize as a vector on a plane. Right? And now, I attach each one of these, and you see, if I attach all the same U1s and connect back, I will get this nice cylinder. Right? But suppose I were to take complex numbers and wind around like this, I will get something like this, right? Right? I will get something like this. Right? Now suppose I wanted to go from the first function to the second function smoothly, I will not be able to. Okay, so I have to show you that I will not be able to do it. So I create a little Mathematica thing. Let me see if this thing works. Sorry, I think I have to. Yeah, it's not coming here. Do I have the Mathematica? Do you see the Mathematica there? Is it called twist? Yeah, it is. Okay. So somehow, I'm unfortunately not able to get it to work when it is static. Okay. So what I have here is a map when I just control the number of twists, right? So you see, I have complex numbers, so I start with S1, and I'm going to twist as I go along, right? So here's a picture of what happens, right? Can you see that? Can you see that? Right? Okay, so let me just, so I have actually done something not right there. Let me comment that out and let me get this to work. Okay. All right. So this thing, I will just move it around. This thing is something with two twists. Can you see that? It has two twists. Right? Okay. Now what I'm going to do is I'm going to take something with two twists, right? And I'm going to take something else with three twists, and I'm going to deform it like this. I'm going to write 1 minus t times one twist plus t times two twists, right? If you want to see the two twist one, I can immediately show you. So what I can do here is I just take NB is 2, and you will see that you will get something with two twists. Yeah, it's just that I don't know why it's when it is static, it doesn't show it, right? You see, it's nicely two twisted ring. Everybody sees that, right? Okay. Now what I'm going to do, I'm going to comment this guy out. And I'm going to show you a case where I'm taking something with one twist and something with two twists and combining it in the way that I did, right? Okay? So this is equal weight of both. It's at half. Okay? What do you see? What do you see? Look at it carefully. What do you see? Do you see that it's pinching off at some points? Do you see that? Oh, see, if I don't press it, it just doesn't show. I mean, I really spent a lot of time trying to get it to show it, but I don't know, some problem with the. You see, see, okay, I cannot point here. Yeah, you can see that somewhere in the middle, you see that it is 0, right? Since I had this problem, what I did was I actually plotted the magnitude of that vector, right, as a function of t, right? So you can see that I'm doing one twist plus, you can see that I'm doing, okay, one twist plus, okay. All right. Okay. Okay, I want to show you two things. So first is, I am doing one twist and two twists. These technical problems are a real pain. Okay. All right. So this is t equal to 0. You can see the function, right? It's called L here. 1 minus L times the one twist one, and the next one is L times the two twist one, right? Okay. What I'm plotting is you see I'm attaching this complex number. So when I sum these two functions, I'll get a new complex number. I'm simply plotting the magnitude of that complex number as a function of the distance on the circle, right? Okay, so you see this, and in my animation is that I'm increasing L. So you see, it starts off, and if I can get it to work, which it died or what? Huh? Plus here. Huh? Here. Oh, thank you, Sudeep. God bless you. Play, yeah? Okay. So you can see that I have very good friends. Yeah, okay, maybe I can just do it like this, no? Okay, what's going on here? Yeah, this is a click here, huh? Here, on the L. Okay, I'm dragging. I'm clicking and dragging. I can assure you, I can't click anymore. Okay, let me try play. Maybe, I don't know. Okay, I'll just quit and come back maybe. Quit. Save. Don't save. Okay, Control Z, PG, CD desktop, Mathematica, twist. Yeah, this is part of the school actually, how to run Mathematica. Okay. Yeah, I'm really sorry about this. I actually tried hard, but. Okay, so let me just do this function definition. Okay, and this. Okay. All right. So what we are looking at is the radius of that as a function of this parameter. So Sudeep, I should just press plus here and press play, right? Now you can see. Very nice. So you can see that there is a one at value of L, it goes to 0. So what that means is that this ribbon is pinching off. Right? Now I will show you that I can combine two arbitrary curves both with one twist. Right? And they will go smoothly to each other. Watch this. This is very interesting. Right? So what I do is I stop this. How do I? Okay, pause. Okay, so what I do, I remove this second twist. Right? This is second twist. Right? Now both the curves have one twist. But I'm going to give a different curve here. So instead of increasing theta linearly, I'm going to increase theta quadratically. Right? But that's still a nice map. Right? So what I'm saying is that instead of theta increasing linearly as you go along this thing, I'm increasing it quadratically. That's all. Right? So now, what should happen? I should be able to smoothly deform, because there's only one twist, I should be able to smoothly deform from one to the other. So the length of the vector should never vanish. Right? So that's what should happen. So I go plus and then do a play, and you will see that the length of the vector will never vanish. Right? Comes down and then goes back. Right? So what have I demonstrated to you? I've demonstrated to you that if it were a complex number that I'm attaching on this, there are these topologically distinct functions. Ones that can be smoothly deformed to each other, and ones that cannot be. And what characterizes them is the winding. Right? How they wind, how many times they wind as they come back. Okay? This object is exactly measuring that quantity. I'm starting from the torus or the sphere. I'm doing a mapping into this Grassmann manifold, and that thing sort of winds around on this Grassmann manifold. Right? Because you can attach different wave functions that it can wind around. Right? It's measuring exactly that. How it is measured is actually quite remarkable. Right? So you can show that these kind of maps from one place to the other, this homotopy, can be made to have a group structure. Right? So two functions which can be deformed smoothly between each other is made like a group element. Then you can take one group element and multiply it with the other to get yet another group element, and so on. So you can actually give it a group structure. Right? This kind of group is called as the homotopy group, right? Of starting from from some manifold going to the other manifold. In our case, what I have shown you, so you should have then asked me, if the base manifold is TD, this should really be pi TD, right? This should be pi TD for the thing here, and for the SD, it should be just basically pi M, whatever is the base manifold. Okay? So there's some magic that happens, and only the SD part is important. So I will come back to that point later. Okay? So I want to show you that this phenomena is actually even more interesting. So what did I show you? I showed you that maps from S1 to S1, which is isomorph, which S1 to S1, which is actually U1, which is the complex numbers. S1 is same as U1, right? They have a homotopy which is given by an integer. So this is formally written like this: pi 1 of S1 is equal to Z. Right? It's actually a group, and it's sort of characterized by the number of windings. Plus winding is different from minus winding. Okay? So you get this group here. Everybody's good? Okay? So now I ask you an interesting question. So instead of going from S1, okay, by the way, I can show you this homotopy group very nicely, right? So S1 to S1 can be demonstrated like this. If I can find my rubber bands. Okay, all right. So you see this is S1, right? This is also a surface of this is also S1, right? So what is, okay, this is not a good rubber band. Right, okay. So this is the Z is equal to 0, no winding, right? So I could do this, right? Right? This is the Z is equal to 1 extra winding, so on. Right? And you can keep doing this, right? And there are infinite integers, so if we keep doing this, we'll spend all the time on that, right? Okay. So now, instead of going to S1, I ask you, I start with S1 and map to S2. So what am I doing? I'm taking my line and I'm attaching 3-dimensional vectors of unit length on that. How many different homotopy classes are there? One class. Why do you say that? Okay, all right. So Chaito is right. So what I'm going to do is I'm going to demonstrate that to you, right? This is my son's toy which I stole, and I'm sure I'll have to do prayashchit later, but we'll see that. Think about that later. Okay. So this is S1, right? How do I define a map from S1 to S2? Well, just do this. This is a map from S1 to S2. So at this point on S1, you go to the center of the ball, take the vector, attach that. Right? You can do whatever you want here, right? You can do whatever you want. But all the time, you can actually shrink it. You can shrink without tearing the rubber band. I can shrink it, and if the rubber band had infinite tension, I can come back to a point. Which means any smooth map from S1 to S2 can be brought back to a constant, to a vector pointing the north. Which means there's only one homotopy class. Which means the group is trivial. It's just identity. So identity meaning additive identity, which is 0. So then we find. So you see, this is mind-bogglingly puzzling, right? You would have thought, right? I'm attaching more complicated things, higher dimensional things, right? So it should get more complicated. But that's not what happened, right? In fact, you will find that calculating these homotopy groups is highly non-trivial if these are small numbers. So in fact, I just went to Wikipedia or wherever it is and lifted some stuff to show you how complicated it can be. Is that my talk? These technical problems are... Okay, let me just start all over again. Okay, CD. Okay, all right. Oh, good, it came back. Okay, so these are the homotopy groups, right? So what I have here, this is all lifted from Wikipedia, right? So those are the spheres. Huh? Those things, those objects, right, pi 1, pi 2, pi 3, are maps from spheres of those dimensions. So pi 1 would mean S1, pi 2 would mean S2 to that object, right? And you see, just look at, say, S2. Just see what happens from, just look at this. Just think about this particular group, right? Pi 12, that is the 12-dimensional sphere being mapped onto S2. Look at the group. It's horrendous. Look at the pi 14 map to S2. Z84. Right? That means it's the Z84 means numbers modulo 84. Right? So they're bizarrely complicated. Right? But you see some magic happens. Right? If you come along this dimension, you go to high dimensional spheres and do maps from smaller objects, you will see that you will get a very nice pattern. Okay? So this is what is called as homotopic stability. So when you go to large dimensional objects and do homotopy from smaller dimensional objects, they start to get some patterns. Right? Why is that important for us? That's important for us because now just from this picture, we can see that if these are small dimensional, if I have a few bands, etc., I can get any answer I want actually, just from this kind of a picture. Right? So if you just think of a two-band model, etc., you may get the right answer in some cases, but it's not generically guaranteed that if I just have two bands and fill it, I will get the correct topological class. So this was the realization of Kitaev and company, that there is something called stability of these homotopies. And that you have to go to high dimensions of these objects, which means large number of bands, infinite number of bands. In that very large number of band limit, these are very precisely characterized. What is large, right? You know, what is the dimension of this and what this should be extremely precisely characterized, right? So once you've satisfied that condition, this entire thing stabilizes. And you get unique answers for depending on what is the spatial dimension, right? Namely, what is the base manifold and what is the target manifold. Okay? And the answer for that topological classification is the following. Okay, I am completely disoriented. Okay. The answer for that topological classification is this. Right? And this is the periodic table of Kitaev. Okay? Now, these classes here, these two classes here, so let's understand what the table means. Okay? And we'll work out this table on the board today. Right? All the 10 classes will work them out. Simple examples to motivate the idea. Right? What does this mean? If I have complex numbers in 0 dimension, which is what Jay had started off his entire discussion with, you can have Z as there can be different Z. So you may ask, what do you mean by mapping 0 dimensional object to that? What that measures is the connected components of that space. Okay, we can discuss what that means later. Okay, and you'll see that you have all these different classes, and in any given dimension, you will see that there are only 5 classes which have non-trivial topology. So this class, for example, class C, for example, is like this case that I discussed here, analogous to this. So the functions, because of the symmetry and what is the nature of the eigenfunctions and so on, that's like this. It has no it cannot support any topology because of the nature of the wave functions and the constraints. There is also this constraint hk is minus k and all coming from the symmetry. So you cannot support any topology in them. Right? Okay. And look at this extremely beautiful pattern. Right? So when you go to the next dimension, what happens? This guy just slides down. And there are two classes. You see, that's why we call them, we colored them in the way we had. You remember we colored them this way? Oh, I didn't have gone there. I can show you this. Right? Right? So these are called complex classes. When you go to the next dimension, this guy slides over and that guy goes up. Right? Again, this is all magic, right? So these are called as complex classes and they will go amongst themselves as you go from dimension to dimension. Right? It's really got to do with some geometry of the sphere and the geometry of this, this high dimensional manifold that we have. Right? And then if you go to the next dimension, you will see that, again, these real guys slide with each other. And there's a very nice pattern to this. So you see, actually, when we drew this picture for the first time, we didn't realize that we had the pattern, right? It's only the way we organized this, magically this pattern emerged, right? So you see, you start with A1, and then you go to BD1, and then you go to D, and then you go to D3, and then you go to A2, C2, C, C1, A1. So whatever is the topological class in this dimension, when I go to the next class, whatever is in the behind arrow, it will pick up the topological class of that. Right? That's what you see here. Okay? And this is all requires large number of bands and all that. Huh? So there are papers which show counterexample for small number of bands and all that. Okay, it's a well studied problem. Okay. All right. So this is the periodic table, and I hope that I've motivated the idea of why. Okay, I've not shown you why there is this periodicity and all. And once you go after dimension 8, you will start repeating this, whatever happened in 0 dimension. Right? And this is called as Bott periodicity. So basically what have we done? We have started from symmetry and we have made arguments as to see which of the, and then we classified fermionic systems according to symmetry and brought 10 classes. In each of these 10 classes, depending on the spatial dimension, they may support homotopically distinct ground states, which means you can have different topological ground states in these classes. And they have this very nice structure here. Right? So that's the main message. I want to add a couple of more things before working out some examples. And Shubhro said I can go for 2 hours, right? So I may take 20 minutes to work out the examples. It's very good. I mean, anyone who feels kind of worn down by things or have very important things to do, please do not feel free. Please, Yeah, okay. All right. So this is what you get, right? All right. I want to make 2 other important points. So suppose I give you a band structure. Right? And I ask you, hey, does this belong to this class? Right? So just take this particular class A. So in the 0 dimensional, there is a particular subclass of that, or there is a set of Hamiltonians in that for which the Z value is 0. So there's no winding. It's trivial. Right? So suppose I give you a Hamiltonian and ask you, hey, is this topological? How will you do that? How will you do that calculation? So this brings us to the idea of what I call as topological invariance, which Jay has discussed. So if you give me some set of wave functions here, there are ways that I can calculate some kind of an invariant. Right? So for example, if you think of this map that I discussed in terms of this map from S1 to U1 or S1 to S1, you will see that the topological invariant can be obtained by finding the winding number. And it's very easy to see what that is. Right? And in fact, you must have seen it all along, right? So it's the following, right? So winding number. So I'm going from integral -1 to 1, say dx. This is the sphere. And I have z of t, or z of x. This is the u1 element. I just take the derivative of this, right? I multiply it by z star of x. And if I want some nice real number and so on, just multiply this by an I. Do an integral, you will get it to a number. You will get it to be an integer, right? And you have seen that this J has actually shown this to be the winding number, right? of a map. Right? So this will turn out to be an integer, and it will tell you in which class it is. Right? Okay, second important point. Some of these topological invariants are actually very important to understand what is topological about this. Right? For example, some of these topological invariants may end up being a transport coefficient. Do you know an example of this? If you don't give the answer to this question, Jayanandra will be very unhappy. Right? So if you take the integer quantum Hall effect, the sigma xy being integer is an example of this. Right? It is the topological invariant which actually ends up being a transport. Okay? All right. Then we can push these ideas a lot further, but I will not do that here. So for example, there is this thing called the bulk boundary correspondence, which Jay has actually shown you many examples of. Right? So if you now create a surface in a topological state, you can get interesting new kinds of phases, new meaning gapless phases there. And you know, they have their own set of interesting physics. Right? And finally, just to make sure that Shubro will reimburse my travel, right? I will make some comments about disorder. Now, everything done here is on clean systems. So what happens if I have disorder? Right? Do all of these things fall apart, or is it all correct, wrong? You know, okay, all right. So instead of going into very technical ways of discussing this, I will discuss disorder in a sense of this bulk boundary correspondence. Right? So what we have seen is that if I have a topological insulator, for example, you know that the surface of it will have a single Dirac cone. Right? It's a metal. Right? And you can, electrons can move freely on that and they won't get scattered and all that stuff. So the criterion for having a topological phase in D dimensions can be reduced, or you can argue that if I take the same system in D minus 1 dimension and put disorder in it, can I localize electrons or not? If I localize electrons, then I will not have gapless states on the surface, which means that the D-dimensional object is not topological. So you can ask the following question: if I take a D minus 1 theory with the same kind of symmetries, is there Anderson localization in that or not when I put disorder? If you can prevent Anderson localization in D minus 1 dimensions with disorder, right, then you have a topological phase, because this thing could be the surface theory of that, right? Okay. So how do you answer this question? This question, okay, it may get a little technical. So this Anderson localization is actually, that problem is reduced to the problem of some symmetry breaking of a ferromagnet or antiferromagnet, whichever you want to. You can think of that as a symmetry breaking problem. This trick is called as a nonlinear sigma model. You can write a theory of localization in terms of something called as nonlinear sigma model. Okay. Now, typically, nonlinear sigma model have gap phases and gapless phases and all that, right? So what do we want? We want completely gapless phases. So what will make a nonlinear sigma model be completely gapless? Okay. For that, you have to add certain terms called as topological terms. And you might have seen examples of this with the spin half chain. Right? The spin half chain is gapless because if you write a nonlinear antiferromagnetic spin half chain, right? If you write a nonlinear sigma model version of this, it actually picks up a topological term. And that will leave it gapless. Okay? The question we will then ask is, if you give me a D minus 1 dimensional theory with the same symmetry class and write a nonlinear sigma model for that, can I add a topological term to that? In precisely analogous fashion, which will leave that guy gapless. And that again turns out to be related to these kind of homotopic groups. Okay? So the nonlinear sigma model lives in a certain coset space again. Right? It's just very interesting to see that the same set of coset spaces will show up in a different order. Let me just go to the transparency here. Right? So you see, these will be the coset spaces of the nonlinear sigma model. Now you see, if you go back and look at these coset spaces and these coset spaces, you'll see that exactly the same 10 families will appear in the other way, but in some different order. And the different order is all, there is a relationship. There is some sliding by 2 and all that stuff. Right? So what are you doing? You're writing a field theory. So you have quote unquote, that field theory is very crudely something like this. You have a particle moving on a sphere, you can write some theory for that. And if you quantize that, it's like a spin actually, right? Particle moving on S2. Right? This particle is moving on this coset space. When it moves on coset space, you will pick up topological terms in its action. Right? The question is, does it pick up a topological term or not? And you can again take some homotopy of that coset space with these as the spaces, and your SD minus 1 as the target manifold, and ask, is that homotopy trivial or not? And that will tell you whether you can add such a term or not. And remarkably, if you do that process, which was done by Ryu and company, you get back exactly the same periodic table as Kitaev got from more abstract considerations. Okay? Okay, so that's the story, right? And now, if you have energy, momentum, or whatever, right? I will work out examples of the zero-dimensional object, and I will show you the topology come out. All we need. So I want to show you that we have all this table that I showed you was not to show my prowess of latexing big, nice formula. That was partly the intention, but not the whole intention, right? So we will use the table that we derived here, right? And actually show topology come out, right? Okay, so let's just start with the simplest case. So I actually worked all this out this morning. Okay, so Shubhro, how much more time do I have? 10 minutes, excellent. Okay, so there are 10 classes, 1 minute per class. Okay, so my entire purpose here is to show you that all that we have discussed is precisely what Jay discussed, right? I really want to make a connection to what he has said, and you should also make a connection with whatever he has said to what we have discussed, right? So that's the intention here, okay? All right, so let's just start with the class A, right? What is the Hamiltonian in class A? What is the Hamiltonian in class A? So the Hamiltonian can be written like this: H0 plus H1, H3, H1 plus I or minus IH2 if you like, and then H1 plus IH2, H0 minus H3. This is the Hamiltonian class A1, AA, right? Why? Because any Hermitian matrix of 2 dimensions, oh, by the way, in my whole discussion, L is equal to 2. Right? What did J tell you here? You recall what was J's topological invariant here? The number of occupied left. Thank you, Abbas. Okay, let's calculate the energies. Can you diagonalize this matrix? If it takes more than like a nanosecond for doing that, you're doing it wrong, right? So the eigenvalues of this. So I think we should make it a crime for any physicist to diagonalize 2 by 2 matrices, right? You should be just able to write it out because this is a spin problem. This is a homogeneous shift of energy, and this is a spin half in a magnetic field, so we know what the answer is, right? It's plus minus square root of H1 square plus H2 square plus H3 square. So what is my space of Hamiltonians? It is equivalent to R4 as a vector space. Otherwise, if you can view it as a Lie algebra, right? But what comes into the energy? Just this guy, right? It doesn't, so the three dimensions of that, they all conspire to give you just this one number. So I can view the whole Hamiltonian, I can collapse this into this. There is H0, and let me just give this guy a name, let me call it H. So this H actually stands for all the other 3 dimensions. Right? Okay. So now let's see. Can you tell me what will be the phase diagram here? Okay, it's very easy. So since I have only 10 minutes, let me just do this. This is 2, 1, and 0. Right? So what am I doing here? So this is H0. I'm just finding the regions where things can be positive, right? So you see that within this, both states will be, if say for example here H0 and H this negative, both states are negative energy. So they'll be occupied. So there are 2 occupied states here. So when I cross this line, I will see that there's only one occupied state, and so on. So now with some imagination, you can see that if I go to higher dimensional matrices, I can get other integers. Everybody's good? So you see I get Z out of this. The invariants are Z. You see? So okay, I'll try to open another copy of this, keep these two side by side so we can do it together. Is that visible? Do you want it to be visible? Oh. What an important distinction. Okay, now I think it should be visible and readable. Okay. I just need the 0, yeah. Okay. I think that's good. Okay? So we have verified, at least to a physicist's satisfaction, that is Z. Okay? All right. Let's go to A2. A3 actually. So these are the complex classes. A3. So for L is equal to 2, what is the space of Hamiltonians in A3? Okay, look at the other table. Right? Look at A3 table. What is it? Hamiltonians looks like this, right? Correct? So what is the space of Hamiltonians? I can just write two real numbers, H1, H2. Right? You give me any two H1s and H2s. There's always one occupied state here, right? Because the energy of this is just plus minus, the minus energy is occupied. You give me any 2 points. Right? I have a path which will go from here to here, which can connect. I'll never close the gap. Right? Look here, if I moved in that Hamiltonian space, I go from 2 bands, 1 band, 0 band, and so on. Occupied. Here, you give me any two complex numbers. I can smoothly find a path which doesn't go through 0. So I can go from one to the other, any two Hamiltonians without closing the gap. What does that mean? This class has no topology. See, it comes out nicely there. Right? A3 is 0. Right? Okay. So Shubhra, whenever you want me to stop, please tell me. Yeah. Okay. So I'll translate that for you. बाद में देख लूँगा. Okay. Let me do a couple of real classes so that, I should actually do one very important class so that you see the Z2 come out nicely, okay? I should do something there, okay? Let's take A1. Huh? Look at the table A1 here. A1, right? What is the Hamiltonian there? The Hamiltonian is complex conjugate of itself, right? So A1, Hamiltonian will look like what? H0 minus H3 plus H3, H0 minus H3, H1, H1. What are the eigenstates? Eigenvalues, very easy, right? So it's H0 plus minus square root of H1 square plus H3 square. Hey, but that's same as this, right? So you get Z out. There's Z out. Everyone's good? Okay? All right. Okay, now let me show you this BD1. It's actually very, very interesting. Let's look at, we did all this work to find the structure of BD1, right? So in our case, P is equal to 1, Q equal to 1, L equal to 2, right? So I have, see the structure of BD1 there? You see it, right? So what should I put there? What should I put for BD1? So H star must be equal to H. So I'm only allowed to put a real number here. Right? I'm only allowed to put a real number in the off diagonals. Right? 0, so you can see that from the dimension, right? See, read off the dimension. P is equal to Q equal to 1. So the vector space of Hamiltonian is dimension 1. So there's only one real number, right? So let me just call that real number H, and 0. And this is the thing, right? Okay? Do you see a Z2 invariant here? Do you see? Okay. Let me take H. What are the eigenstates? What are the eigenvalues? It's plus minus mod H, right? Right? So let's say that H is positive. If H is positive, the minus H energy is the ground state. If minus H energy is the ground state, what is the wave function? The wave function is 1 minus 1. Yeah, 1 minus 1, right? 1 by root 2. 1 minus 1 is the eigenstate of sigma x with minus 1 as the eigenvalue. Right? So the states here are characterized by minus 1 eigenvalue of the sigma x operator. The state here, always the number of occupied states is 1 except at this point of 0, right? Where 2 of them will become degenerate. And that's a quantum phase transition from the topological sector with minus 1 eigenstate of sigma x to plus 1 eigenstate of sigma x. So you see that the invariant is Z2. So it's what is the parity of the occupied state. And Jay has actually very nicely explained all this. He explained this in terms of BDG, right? And he talked about fermion parity, but we don't need that. I mean, you just need the parity of the sigma x operator. So it's a Z2 invariant. Right? Right? Throughout, except this quantum phase transition point, where the gap closes, right? You have fully gapped and one occupied state. And what determines the topology is the parity of that occupied state, if you like. Okay? Okay, you can immediately see if I go one class down, D, right? D is Z2. And you can see the structure of D from whatever we have done. Just go to the fourth column there. You will see that it is exactly the same thing, the class D, except that this will look like minus IH. So it's exactly same as this. This is the class D. The Hamiltonians in class D will look like this. Right? And you can see it's exactly same as that, and therefore it's Z2 again. Everybody is good? Free. Yeah. Okay. So that's what happens. Okay. Now let me show you. Okay. You should actually work out the trivial ones. It's actually very interesting to work out the trivial ones. You should definitely do it. But let me show you the non-trivial one. Say class A2. What is the class A2? Sorry? That's correct. But if time reversal symmetry with t square equal to minus 1 as was. So do you know any if in 3 dimensions the A2 class has this what is called a standard topological insulator? The Z2 topological. Okay, so we are talking about that. So let's write out what is the Hamiltonian for that. Can someone tell me what is the Hamiltonian for A2? This you should be able to say without looking at the table. Okay, so the Hamiltonian for A2 is magically just this. Right? Because you know that this is spin half. Right? You know time reversal symmetry shouldn't be broken. So there cannot be a magnetic field. So all it can have is the energy of where this level is. So that's the Hamiltonian. What are the eigenvalues? Right? And either 2 are occupied or both are empty. Right? So if you have a bunch of states, it will be 2Z. You see, it's 2Z. Right? Okay? And you can work through other classes and show that they are trivial. In fact, with L equal to 2, some of the classes don't even exist. Right? Because some of these things will require at least 4 orbitals. Okay. So here's an exercise for you. Right? Take L equal to 4 Hamiltonians of this kind and find a way to classify their phase diagrams. Or find a way to draw their phase diagrams in all classes. How many different, so you should be able to reproduce this table. Right? If you choose L equal to 3, then many classes will not exist. Right? Okay? All right. Let me conclude by saying a couple of things about what are the open problems in the field. Right? So we certainly know how to get the structure of the Hamiltonians, or we certainly know what are the 10 classes based on symmetries. The next question is, if I put in interactions, what happens to this table? What happens to this periodic table? So for example, if I take a 1D chain, right, and look at this class, this is the Kitaev chain, the non-interacting problem has a topology labeled by Z. When you put in interactions, some magic happens. I certainly encourage all of you to read this paper by Fritkovsky and Kitaev sometime in 2010. The classification collapses, quote unquote. Instead of being Z, it becomes Z8. And this comes from some fusing of some Majorana fermions. Okay? So you actually should go and look at that. And so the open problem is, what is a general framework in which we can actually classify interacting topological cases? Is it even, okay, I don't know. So this is an open problem. There are many ideas, there are many interesting ideas based on group cohomology and all. And actually I did the group cohomology here so that some of you who are interested can actually have a starting point for that. So there are several ideas in the field, and I hope some of you will actually pursue them, and maybe in fact may not pursue them and come up with your own ideas for classification and write some fantastic papers. So, okay, yeah, there is. I mean, so fractional Hall effect would be what would be called as long range entangled things. So these classifications are what typically have a short range entangled things. Yeah, maybe we can discuss offline. Yeah, okay, thank you so much.
Essence.